Okay, if we go back a couple of lessons, or not a couple of lessons, but a few slides, and we look at some of the transformations, okay? We're trying to graph this, try and point at it for you, Zach. We're trying to graph this function here, okay? And we're going to graph that by using a transformation of this parent function here, okay? Now the parent function 2 to the x, we already have the black dots on the graph that represent those, such as 2 to the 0 equals 1, 2 to the 1 equals 2, 2 to the 4, 2 to the second equals 4, 2 cubed equals 8. So those values are on there. And then we did the transformation to those values. What does the negative 4 do? When the negative 4 is down in the front, not up in the exponent, it causes a what? Okay, we're going to have a vertical shift of 4 down, which is exactly what we have here now with the red dots are all exactly 4 down. Okay, today is going to be pretty quick because the only thing we're going to do we can get there, is this number that we just talked about here, that E is a value that if we calculate the interest for $1 at 100% for 1 year, okay, and we do that n times per year, and we want to figure out what happens when n gets larger and larger, okay, we just showed on the graphing calculator how that value approaches this value down here, which is called E. E is Euler's number, okay, it was created or found out by him, okay, it's a non-terminating irrational number with the value 2.71828 and so on. All we're going to do is we're going to learn how to use our calculators and find the letter E, okay, so we would do that, so you should have a calculator with you. The E button. Anyone find the E button? The E value button? Where would be a thought to find it? Maybe by pi? And if we look over there by pi, pi is right above the caret, E is right above the division sign. So if I want to take E to the 3rd power, I go get that number E, okay? And if you want to know what E is, you can just hit E and hit enter, and there it is on your calculator, 2.781828. Okay, if I want to raise that value to the 3rd power, I can then hit the caret button and a 3, and you should get a number 20.0855. If I want to raise it to the negative 0.23 power, okay, I grab my number E, I hit the caret, then enter negative 0.23, you should get 0.794533, and so on. What do you think E to the 0 is going to be? It should be 1. Anything to the 0 power is 1. How about E to the 1st power? That should just be E then, shouldn't it? Okay. So those are the values that you should come up with. Let me put them on the board for you. E cubed was 20.085. And so on as it continues. To the negative 0.23, 0.7945, and so on. E to the 0 is a 1. E to the 1st power is actually E, which is 2.7, not with another decimal. 2.71828, and so on. E has a big part in exponentials because E has a big part in logarithms. Okay, you guys did some logarithms in Algebra 2. Okay. We have two types, well, there's many types of logarithms, but the main two is common log, which is a base 10, and then the natural log, which is a base e. Well, since we have natural logs with base e, we are going to talk about exponential functions with a base e, because the next thing will be to get into the logarithms. So the only thing that's going to change is when I go to graph the function e to the x power, is it really any different than graphing 2 to the x or 3 to the x? No, other than the numbers are going to be ugly, okay? You know, if I do 2 to the x, I have nice, easy numbers, like 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4, nice numbers, okay? That's the only thing that's different. 3 squared, or 3 cubed is 8. 5, 6, 7, 8, one down from there. Okay? The other thing that's so nice is over here is 2 to the negative 1 is 1/2, 2 to the negative 2 is 1/4, 2 to the negative 3 is 1/8. Nice, simple, easy numbers to find and remember. Okay? What we have to do is we got to come up with some values with base e to help us out. Okay? Well, let's start with just 2.7, which we'll use actual e. What's 2.7 to the first power? It's going to be e, or 2.7, right? So for our purposes, am I going to be able to graph, 2.718 and make it look different than 2.7? I'm barely going to be able to guess for 2.7. So we put 2.7 to the first power at approximately 2.7, okay? If I have 2.7 squared, well, let's go figure out what e squared is. So if we grab our calculator, punch in e, square it, we get 7.389. Let's call that 7.4, approximately. Okay, e to the third power is going to end up kind of getting off of our screen, because you see it's almost 3. 3 cubed is 27, so 2.7, or e raised to the third power is up over 20. It's 20.08, or about 20.1. So, knowledge of what it is, yes, about 20. Is it going to fit on most of our graphs? Probably not. Okay, now if we start taking 1/5 of it, because we're dilating it by 1/5, then remembering that it's 20 and 1/5 of 20 is about 4 will come in handy. Okay, but other than that, not so much. How about before that? What's 2.7, or e, I should say, to the 0 power? That's going to be exactly 1, so that one's going to be fairly nice. How about e, which is about 2.7 to the negative 1 power? Well, close to 3. What's 1/3 to the negative 1 power? Or I shouldn't say that. What's 3 to the negative 1 power? 1/3, so it's going to be awfully close to 1/3. If we actually punch it in, e raised to the negative 1 power, we get 0.367, so about 0.4 we could call it. And they're just going to get smaller and smaller faster than the 1/2 did. E raised to the negative 2 power, we're at like 0.13. Now again, I'm writing 2.7 every time down this list. It's really e. Okay, we're just using the 2.7 to help us visualize. 2.7 squared, we just said, was approximately 0.135, about 0.14, so very small. So if we wipe out these nice dots that we had for the base 2, and now we need to fill in our dots for e. Okay, let's start with the easy one. E to the 0 power. E to the 0 power is going to be 1, so that's going to be a very base point for us. E squared, which is right here, is 7.4. So e to the, let's do e to the first power first. E to the first power is going to be 2.7. So when x is 1, we're going to be at about 2.7. Okay, slightly above 2.5. E squared is going to put us at 7.4. is slightly below 7.5. Those are gonna be kind of your main 3 points. Then the other ones on the other side, e to the negative 1 power is 0.4, which is slightly below 0.5. And then we're all the way down to 0.14, which is very small, just slightly above. Very much the same graph, just the dots are slightly irregular. Same exact type of graph though, we're going to be starting down here, rising up through the 0, 1, and increasing as we go to the right. So now, if they ask us to, and on this page it has all those numbers that we just had, okay, for you to see in your notes. And it has the points themselves on your graph, which are very similar to the 2. Now they're going to ask us to do some transformations of base E. So they're asking us to graph this guy here. What kind of transformation is that going to give us? What kind of flip or something? Okay. Basically, they multiplied the x by -1. So therefore, comparing it to the base e to the x, e to the negative x, they multiplied the x by -1. Multiplying the x by -1, first of all, multiplying by -1 is a reflection, and multiplying the x by -1 is a horizontal reflection. Therefore, we can find the dots by simply reflecting them across the y-axis. So, starting with over here, we're very low when we're out here with the input of -3. Slide that over, and we're going to be very low when we have an input of +3. Our input of -1 puts us at 0.4-ish. So now we reflect that over, and we're going to be on this side. Our 0, 1 is not going to move. Reflecting it from the y-axis stays right there. Our 1, 2.7 slides over to -1, 2.7. And our 2, 7.4 slides over to -2, 7.4. And we simply do the best we can drawing our exponential function transformed from e to the x. Here it is with red dots with the values over there. And up here it talks about how it's a horizontal reflection over the y-axis. Could we every single time plug in values? You sure could, but it's going to take you a lot longer and it's a lot nicer to use your transformations. Alright, how about this guy here? They want us to graph e to the -0.5x, and we're going to do that by comparing it to f of x, which is given to us over here. F of x is the red dots, which are the same red dots we had previously. You know, e to the first power is 2.7, e squared is up at 7.4. Alright, what does a -0.5x do? What do we got? Okay. First question I have when I look at transformations, is it addition and subtraction, or is it multiplication and division? This one's what? Multiplication, okay? So addition and subtraction is translations or slides. Those are easy. These aren't the translation. This is a multiplying by 1/2, so it is a dilation. But I'm multiplying the x, so what kind of a dilation is it? Horizontal, okay? We remember back to our functions that if my function was, let's say, the x squared, okay? If I take the entire function times some number, it is a vertical dilation. If I take the the input value x and multiply it by a value before I do the function square it, it's a horizontal dilation. Okay? What's the other thing to remember? If it is a vertical dilation, it is what it is. So multiplying by 2 is going to be what kind of a dilation? It's going to be a stretch of the old graph. Every point is going to be 2 times as far away from the x-axis. But what happens when we're inside? That's where we get that seemingly the opposite stuff, right? So if they say +4 inside, we end up actually moving 4 to the left, okay? Well, if they multiply by 2, you may think everything's going to be twice as far away from the y-axis by stretching it horizontally. In reality, it's going to compress it by a factor of 1/2 or 1/2. Therefore, if I had 1/2 x squared, and I'm just using squared because it's an easier one for us to think of, okay? 1/2 x squared, I'm still multiplying, and it's still inside, so it's still horizontal, but seemingly the opposite. You would think 1/2 would compress it towards the y-axis. In reality, it's stretching it twice as far away from the x-axis. And if we look, that's the guy we got up here, isn't it? We're multiplying the x by 0.5, which is like 1/2. So it's going to be a horizontal dilation. But since the number is 0.5, we are going to be dilating by a factor of 2. A horizontal dilation by factor 2. So all my points should become twice as far away from the y-axis. Remember, it is a horizontal it is a horizontal dilation. Okay? So let's do we'll do it in green here. So let's dilate first, because there's more than one thing going on up there, because it's negative 0.5, not just 0.5. But every one of these points, these 5 red points that we have, we need to dilate twice as far away from the y-axis as they are. So if I start with this point out here, that is 3 units to the left and just a sliver up. He's got to go to 6 units to the left and just a sliver up. This other red dot that's 1 to the left at -1 and like 0.4, I believe it is. Okay, he's got to go out to the -2 and 0.4. This guy at 0,1 is going to stay because twice as far from 0 is still 0. Then this point that's at 1, 2.7 needs to slide out to 2, 2.7. And then we slide up here to the 2, 7.4. He's got to go out to 4, 7.4. So right now, because of the 0.5, our red points have become the green points, but we're not done. What's that negative going to do? Okay, that's going to give us, again, it's on the x, so it's going to be a horizontal thing, and multiplying by -1 is a reflection. So it's going to be a horizontal reflection. Okay, so we'll use blue for the new points. Now the green ones are where we're at. So this point way out here, 6 units to the left, needs to be reflected over, so it's 2, 4, 6 units to the right. This point here, that's 2 units to the left. This green point that's 2 units to the left needs to be reflected, so it's 2 units to the right. Again, our 0,1's not going anywhere. My green point that's at 2, 2.7 needs to slide over to -2, 2.7. And my green point way up here that's at 4, 7.4 needs to slide over to -4, 7.4. So my actual final graph will look like so. Quite a bit more stretched than the original, if I hit my dots. The original one is in red. You can see the blue one has been horizontally stretched out. It's stretched left and right. Okay? next page kind of shows, I guess, in different order with the colors. The red was the originals, the blue was the horizontal dilation by factor 2, and then the green ones were the new ones. Okay, how about this guy here? Here is our parent function, e to the x. We would like to do the transformed function, e to the x plus 3. What's going to happen here? Okay, each point should translate 3 to the left. Again, it's adding to the x. That's a horizontal change. Adding 3 seems to be to the right, but seemingly the opposite. We need to go to the left. So we would have our new points. This guy down here would slide 3 to the left. This one here would slide 3 to the left. The one at 0, 1 would slide 3 to the left. Each individual point would slide 3 to the left. So again, the original e to the x graph is going to look like so. The new transformed graph will look like so. And they are the same graph, just transformed by translating 3 to the left. There's a new one. I didn't have the old one drawn. There's a new one. Again, they're not straight lines, they're curves, but again, I was doing this at home and I have to go with what I have at home. Got to connect them with straight lines. That is it. So we'll see if the recording worked. So do I just click that button on the bottom? I believe. Stop.